Out, and congratulations for making it, to the last talk of the entire conference. Well done, well done. So today I'm going to talk about data science using FHIR data. We're going to talk about some approaches that we're taking to do that sort of thing, and then actually do probably the most daring thing you can do in a tech talk, which is actually a live demo of an open source system that shows some of these patterns in action. So we'll go ahead and jump in here. Now, we'll start with an architecture or a pattern that probably seems familiar to a lot of people in this room, in that you have some sort of transactional database, some sort of operational store that's optimized for your applications, your services, everything you need. Then, on the other hand, we have a database for analytic workloads, which tends to be structured and optimized in different ways to kind of handle those sort of large queries before that. So fairly common stuff there. And then, of course, in the middle, we have a big, complicated ETL process that basically nobody understands, and it takes a lot of high-touch human knowledge to get in there. It's I don't know if there's a name for this architecture pattern, but I feel like there should be, because it seems to keep happening. And even starting out, it's never intentional, right? We'll start out with these two systems which make complete sense because there's different trade-offs between these workloads. But it tends to evolve on that. As we have new needs for the analysis, new data sets, new things we want to transfer, just the complexity grows over time, and keeping these things in sync is a challenge. And not only is it a challenge with regards to just all the code for all the ETL and all that work, but it's also a challenge in terms of the growing gap between the data that we're working with in our online systems and the data in our analytic systems. So if I want to do something where I might identify some cohort of patients, or I want to identify some group that I want to apply some intervention to, or engage in some care management program, if I'm doing that on an analytic database and it's skewed, it's different from what I'm actually running in my production system, my transactional database, suddenly everything I do from an analysis side I have to re-implement or translate or bring back in to where it can make a difference, where it's hands-on. And so this gap between our analysis and our online systems it's a real challenge, and something that we constantly are having to address. And so this being a FHIR conference, I think that we want to look at it a little bit differently, where we have user applications, we have our analytic applications, machine learning workloads, or anything else, just all living on top of that underlying FHIR data model. And the idea being there is, if I identify something in my analytic workloads, I want to be able to apply it by speaking the same language everywhere. And another way to put this is, what if we could make FHIR data really easy to use by the best available data science tools, and to make this sort of technology disappear and make it easy to work with? And by that I mean, one way to look at it is just, what if we just made it so we could take native SQL and directly use our FHIR resources at scale? So our data scientists, our analysts, this should look pretty familiar to them. There's nothing specialized here, with one exception that we'll touch on. It's just SQL. It uses some nested structures, but the nice thing is that many modern SQL engines actually support this. And we can actually map every single FHIR reference, every single FHIR field, everything that we have in it, into an engine that can be run like this. And we'll jump into some specifics on how this can work. So that's just one example of where we're just gathering observation LDL information. Here's another one that's a little bit more involved. And what if I want to identify pre-diabetics? In this case, again, just standard SQL using these FHIR resources being run over very large data sets. And then once we have that started, our SQL, we want to bring it on to what are your favorite data science tools, and just kind of build this out to show a handful of the things that our users like to work with. And of course, the list goes on and on. And this opens up another real challenge that we face in terms of applying analytics in healthcare, is that there is not a lot of consensus on what the best tool is. And in fact, there isn't any single best tool, period. It really depends on the problem that you're working on and the challenges that you're solving. So we really want to support a rich set of these things. And even if we could build consensus on what the right tool is for a specific sort of analysis, something else is going to come out in a few months, and all the stack's going to change. So we want to be able to take FHIR, we want to make it so it's natively usable by popular tools that are SQL based. Then we want to be able to make it also so I can integrate it very easily with a variety of front ends, with a variety of analytic tools. And this sort of implies that part of this system, as it grows, as it evolves, is we want to maintain this separation of tools and data as much as we can, because our data is essential, but we want to be able to quickly iterate on the tool sets that we're building on top of it as we go. And really in between there is some sort of data catalog or data dictionary. And we think that the FHIR standard actually is a really promising way to manage this dictionary. But what does that look like? And how do we do it in practice? Well, let's take a look to show some of the struggles that we're dealing with here. If I just click through this, this is actually the FHIR condition model. If we expand out all of the optional fields and all the types in it, this is, I mean, there's several pages of goes on and on. This is just the condition model in itself. And this is kind of interesting because, I mean, amazingly, this looks complicated, but in a way, it's so much simpler than, it's actually really well curated, it's really well thought out. There's been so much effort to put into creating this data model that makes a lot of sense for the vast majority of use cases. So it's great, but at the same time, we showed those list of tools, we showed those SQL queries. It can be very difficult to actually natively work with this complicated data structure in a way that meets the needs of our analytic users, that really is easy to work with, that's really natural to work with. And so kind of the way that we think about this is we think of a person record, think of a patient record, think of even that condition model, and you can kind of think of it as a shape in a very high dimensional space. And so we can take that and we just want to create the view of that underlying condition model that makes sense for the problem at hand. We project it on from our massively complex high dimensional space into something that's a lot smaller, that's a lot simpler, that's a lot easier to work with. So we start with conditions, or let's say we're working with observations, which is probably even more complicated. We want to start with that, but then we want to be able to project it, with a simple table. We've gone from our observation model, which is very high dimensional, to this very much lower dimensional space of here are the LDL values for everyone in this system in the 2017. And so kind of, sometimes I feel like a lot of times what we're doing in terms of this deep analysis space is really just taking everything that we have and converting it into giant spreadsheets. And it is kind of tongue-in-cheek, but once we have that, once we have a query that looks like this, once we can project it onto these lower dimensional spaces, then it becomes much easier to work with in terms of any off-the-shelf tooling can analyze these values. So where do we start in terms of building this system? And since we're in FHIR, I think that the most important thing that we'll start with is that we'll start with the structure definitions. This is our shared understanding. This is our shared data model. Whether I'm building an online application or doing some deep analysis of data, the structure definition is our source of truth in terms of the data model. So that way we can not only, we have the same models everywhere, but we can make them portable. And then it actually touches on another problem that that's a real challenge, in that reproducible research or reproducible analysis across systems. This is actually just a huge problem just in general, of like we produce some sort of outcome and we can't reproduce it, or we don't even know if it applies in other contexts. And then once we even if we can reproduce the system, having to implement that over an entirely different data model just opens up many sources of errors. So we kind of start by this same fundamental language, both for our online and our analytic applications, and let us reproduce it. And the nice thing is that since FHIR is really a logical data model, we can project it onto different physical data models that lend itself to these workloads. So FHIR by itself has JSON and XML representations that are pretty heavily used. There's an RDF that's less frequently used. A protobuf representation. I see my friends at Google back there. So but it's really the same model. It's just an alternate representation that fits those needs. And then we're also going to touch on, one of the things we'll do today is we'll look at FHIR data stored actually Parquet files to help meet these analytic workloads. And I want to mention that this last one in particular, because we'll focus in on about it, is like there are trade-offs between all these data models. They fit different things better. Here we're talking about Parquet files and actually storing that logical FHIR data model in a columnar format. Because typically, like whether it's a JSON file or an XML file or a CSV file, our data is written like this, and that every row is physically stored next to each other. So you have columns A, B, and C, or even if it's a JSON file, it's items right next to each other. And this is great if your predominant access pattern is to actually load up the entire record most of the time. So if I want to get A, B, and C, they're physically stored next to each other, I can grab that off disk really efficiently. But it doesn't work so well if I have a billion rows and I want to be able to scan field 1 for some subset of them that meets criteria. Basically, I'll hit A, then I'll skip a bunch of, my disks will just skip up to D and then skip to G. And so there's a lot of inefficiency by just simply skipping all these things I'm not interested in. So one of the things that we'll show in this demo is actually take FHIR data, and instead of writing it in a row-wise model, we write it in a columnar model. And so if I want to just scan my observation code, I can do top-to-bottom disk reads really, really quickly, since everything's physically stored next to each other as I do these scans. And we've actually gotten some pretty remarkable performance out of this by doing this in terms of being able to scan literally billions of rows in single-digit seconds to do this sort of query. And this is without any external indexes or anything. And in fact, this is kind of like one of the core ideas behind this sort of system is there isn't an indexing model on top of it. Because what we want to do is we want to allow our analysts, we want to allow our users to ask any question that comes to mind about the data. I don't want to pick up the phone and say, oh, we need to create a new index on this particular table because my queries aren't working. I mean, the indexing model is really useful for a lot of use cases, but if I'm asking novel questions frequently, or if I don't know upfront what questions I'm going to ask about a data set, then you don't know what indexes to build. And so as a result, we want to store these resources in a way that I can scan them efficiently without having to have a bunch of pre-built indexes. And that's one of the advantages. That's really one of the key features of using these columnar formats. We touched on Parquet, but there's a handful of others as well that builds on this sort of thing. So we're going to take a look at a demo. So this is actually an open source project. I'll have links to it later in the presentation as well, of doing this sort of analysis on healthcare. And everything in this demo, by the way, is available in a Docker container that you can download and run yourself for anyone interested. So we'll go ahead and skip over here. Actually, I'll just bring up I'll share this link later in the presentation as well, but there's just this Bunsen tutorial up on GitHub. So this project itself was actually a combination of FHIR and the Apache Spark processing engine. So we called it Bunsen because it kind of named itself because of that. So what we'll do here is and you can, if you want to run this yourself, you can just grab this GitHub repository, and then all you need is Docker to be running, and then just launch it from this command. So I'll go ahead and launch this thing myself. Actually, I think I probably have it from an earlier run. All right, so we'll go ahead and launch the system here in our Docker container. Open it up. Okay, so here we just launched a Jupyter Notebook. So if you're not familiar with Jupyter, it's really just sort of an online interactive programming environment based in a web application. And when you first bring up this demo, I'll open up the getting started phase for it. So if you want to work through this on your own, you can just open this getting started notebook and kind of run through it. And all this does is import some example data, some test data that we use for demo purposes. All the demo data actually comes with the tutorial project, and it's all actually generated with Synthia, which is a really incredibly useful tool for doing this sort of thing and packaging it all up. So yeah, the first time you run this, then you'd run this getting started notebook. But I've already run this, so for the sake of time, I'll just go into our data engineering tasks within this system. All right, so we'll go ahead and first thing, we'll just have some housekeeping here to get the system started. So right now we're running Apache Spark all within this local environment. We actually have this exact system running in production in a pretty large Hadoop clusters in a variety of environments as well. The nice thing is that all of this code is completely reproducible across these settings. So just the exact same thing I can run locally, we run at a much larger scale over many billions of rows in our production environments. So this one is just setting up the local Spark cluster, all running on this machine. So the first thing that we'll do here is we just want to look at the data that we have that we want to analyze here. So in the previous notebook, we imported a bunch of stuff from Cynthia. And what you'll have here is this data catalog where each table is basically just the FHIR resource representing the data that we imported. So you see allergy challenges, care plan claims, so on and so forth. So we just have a dozen resources that we somewhat arbitrarily grabbed from the Cynthia data that we loaded. And I think this is the sort of user experience that we really want to give our data scientists, in that normally they would log in the system. We tend to group our databases in ways that can be just different collections of data from different systems. And then they can immediately see everything that they have there. And one nice thing is that each one of these things is fully defined by the FHIR resource. So if you want to know what the observation data model is, for instance, you can kind of just go look at the FHIR documentation for it. The next thing that we have that's really, really useful is in terms of, let me make sure I run this cell, is value sets is pretty central if you've ever done anything significantly with working with FHIR. Just the ability to specify and work with value sets for so many operations is pretty important. So we actually built in native support for working with value sets in this. So we just kind of we basically publish these value sets to our processing cluster and use just an alias for it that we reference later. So there's a couple examples here where we might just have value sets in these cases are just simple code values. In other cases, they may be like value sets that were just published from a terminology server. So in this case, this is actually the example value set that is with the FHIR documentation that we just kind of published for there. So once we have the value sets published, then we can actually just start running our queries from it. And so I think this is kind of neat here, right? And so we go from the condition table. In this case, we're looking for code values that are in the coronary heart disease value set, and there's our projection from it. Here's another example. In this case, jumping into observation tables. And so we can actually do things within the inspect this table. So if I, for instance, let's say I do Spark.table observation, and then I can actually print the schema of this. So you see the full schema of that observation table directly in there. And one thing that's, because we're strongly based on the FHIR data model, if I actually open up the observation resource here and reference like the documentation, so you say, the category, code, subject, and so on, you can see exactly the same fields represented in this underlying data model here. Scroll up, there you go, code, so category, code, subject. All these fields are directly in our data model, which provides a nice reference because the FHIR community has done such an excellent job in defining and curating these resources that typically our users will just go over and look at this documentation to figure out the semantics of all these sorts of things. And the other thing, though, is that, like we mentioned before, is this is quite a complicated underlying data model. But again, we can just project it onto a much lower space, and here we go, in a much simpler table that works with it. And once we have this simple table that we can work with, then it becomes, just using off-the-shelf tooling becomes really simple. Now, in this environment, I wanted to package everything up in a single Docker container, so it's a really small value space, but the same thing works over a much larger cluster. So in these cases, I just want to do, say, some descriptive statistics of my LDL values. We'll just describe them, and in this case, you can see two pandas there. So if you're not familiar with the sort of the Python ecosystem, pandas is just a table, an internal data frame library that natively renders in these notebooks. So we'll take it and we'll just display it there. So that's why you'll see those two pandas sort of strewn about this code a little bit. And here we can kind of get a rough idea of our statistics, our min value, max values. This next one, or we can just sort of graph the distribution. And like I said, it's a small data set, so you can kind of, it's a little bit chunky, not a ton of values there, but you can kind of understand the distributions of our data sets. So this is our starting point, and you can tap into whatever other data models that we're interested in. I mean, I could change and affect that. I mean, if I wanted to change the year, I can kind of interactively get this sort of experience. And I mean, the really nice thing is that because all these operations parallelize so quickly, I mean, I can get very similar performance to this sort of interactive changes. Like, so actually, I think I published HDL as well. So I can just kind of go on the fly and experiment with these things as we go. And so even at a much larger cluster, I can do this sort of quick analysis, with similar response times, because it parallelizes the workload against many machines. And the other nice thing is that as we create these tables, we'll frequently can cache them in memory. So if I'm interested in these HDL values, I'll just save them, I'll pin them in memory in the cluster, so I don't have to recompute or rescan disks every time we do that. So it really creates the sort of experience that we want to provide to our data scientists, in that everything is just there for them. They can project it onto whatever data models they want, and they can work with it directly within this environment. All right, so let's do, I think that sort of gets our sort of exploratory task. Let's do something interesting with these data sets. So this next step, we're going to look at an example of actually building a cohort, and I just put in somewhat arbitrary criteria here that reflects patterns that we might see often. So let's say we want to find a group of diabetics we want to analyze. So we're interested in folks that have either diabetes or a condition indicating pre-diabetes, or an elevated HbA1c value. And then we want to see they also haven't joined, haven't had a wellness visit in some time. So you can imagine that we have this repository of a large amount of FHIR data all joined together, and let's see if we can answer this question. And the pattern that we kind of see emerging a lot of the times is that story that we told a little bit earlier, in that we have the condition model, this very complex high-dimensional space. So let's just start creating views on top of our underlying data model that match the question that we're trying to answer. So the first thing that we want to do is in this question that we asked is who are our diabetics? So let's just build a table of who our diabetics are. We'll do it right in line in this tool. So here's our simple SQL, where we're just selecting the condition, or the person, or the code values, and then we're going to grab anyone that's in the diabetes risks value set. And this just includes the code values that it's a standard FHIR value set that we had referenced up above. And we go from that, we create this table of all the person IDs that have an indication of either diabetes or pre-diabetes, and you can see the specific SNOMED code values right in line here. Okay, so we have a building block. We've taken our complex data and we have one part of our question. So let's just keep going. What's the next part of our question? We're also interested in people who have an elevated HbA1c value. Okay, so now what we're going to do is we're going to build the next building block to help answer our high-level query. So we scroll back down, and we'll go ahead and run this query to find people with a high HbA1c. So similar pattern. We're selecting from observation. We're looking for within our HbA1c value set. We're looking at our quantity of greater than a certain threshold, and we'll check for only final status. So we'll query all of our observations. In this case, it's quite small, but in general, maybe much larger. And here's all the person IDs that have an elevated HbA1c value in this system. And so now what we can do is, if we recall, like the question we wanted to ask is we wanted to find everyone that either had a diabetes condition or a high HbA1c. So we'll just take the two building blocks that we had, and we'll just create a union of them. So we'll basically union all the person IDs in this one with all the person with diabetes conditions. We'll make that distinct because we don't want to have duplicates in there. And then we'll go ahead and run that. So based on top of our building blocks, okay, so we've now identified like that part of this set of people that we'd be interested in. And then the final piece is we want to find anyone who hasn't had a wellness visit in some period of time. So we'll just keep building these building blocks. In this case, if you want to find people who didn't have a wellness visit, what we'll do is we're going to find everyone who did, and then basically do an anti-join between our diabetes and people who've had wellness visits to find everyone who didn't have it. So we're basically selecting from our encounters There's the class code, which again is defined, documented as part of the FHIR profile within this period of time, and we can create this piece. And as I go through these things, I talk about building these pieces to answer our higher level question. I think that there's something else that's important to mention in here, in that every one of these queries that we're doing here, by building these tables, we can actually inspect, analyze, debug, troubleshoot, do data quality assurance against each one of these building blocks. Because if you can imagine like a report that says everyone in my cohort, here's a big list, and you're going to ask, well, this doesn't look right, or why is this person there, why is that person not there? By expressing it in this pattern of taking our very complete yet complicated FHIR data sets and then start building these simplified projections, we can actually do analysis of each simplified building block, each projection, independently of the other ones. So if I think there's something wrong with, say, my wellness code values, for instance, I don't have to keep in mind my entire cohort definition when troubleshooting or doing any sort of statistical analysis of this data. I can just take the underlying encounters and I can look at this in this particular space. So the result being is that we can be much more confident about each piece of this larger complex query that we're building by analyzing it independently in smaller units. And then, as we gain that confidence, composing them together to answer the bigger statistical question, the bigger analytic question that we might be working with here. So in this case, we have our wellness visits, and then we'll finally kind of jump into closing that out. We'll simply take our diabetes risks. We'll do an anti-join with the people who had wellness visits, and then we have it. We have this list of people that are either at risk of diabetes, have diabetes, and haven't had a wellness visit in some period of time. And of course, this is just fully reproducible in any environment. And we can keep on sort of building on top of these sort of patterns by asking these questions. So in this next one, I'll go through this somewhat fairly briefly, but the next thing that we often want to do is for a variety of workloads, whether it's a machine learning workload or just a lot of analysis, we want to build turn our data into a time series. We want to tell the patient's story over time. And so in these cases, we can just use simple SQL to build that time series as well. And this query looks, I might zoom in a little bit, but this query looks kind of complicated, but if you read it from the inside out, it's actually not too bad. So what we're doing is like if, let's say I want to compute the average HbA1c level. So if the observation value is in the HbA1c value set, we include it in our average, otherwise we include null. And the SQL average function simply ignores null values. And so we have the HbA1c value, and we can do that for a number of ones. And then since we're grouping by the subject reference and somewhat arbitrarily a year and month, this is basically just creating the average of each one of these lab values for every year and every month and every person in the system. So if we run that, and you kind of see what we produced here is like, so you can kind of see this first step into our time series type model where we'll have the year, month, and we'll have the average of these different lab result systems. And in fact, this is very similar to a pattern that we use for a lot of our analysis. We'll have many hundreds of different lab values that we kind of aggregate in this manner. But once we've gone from the underlying observation model, again, we've entered a tabular form. It's a time series type structure so we can understand the changes, understand the flow of patients over time in this system. And we just keep on iterating on this same basic thing. It's like we have a bigger question, break it down into these smaller pieces, and then create these views of the data to answer those pieces. So in this case, let's say our time series wants to detect the recorded instances of various conditions. Well, in this case, we'll do something very similar, where we just look for, if you're in the hypertension value set, include it, otherwise don't. And in this case, the semantics of max is true is greater than false. So it will include only things that have a condition registered during that month. And then we'll just grab some patient demographics and we'll join all this stuff together. And sort of the finale there is like, we've gone through just in this notebook, taking our massive repository of FHIR resources and then creating a time series that includes lab values, it includes demographics information, it includes condition information. Then we can just plug this in. And then from here, oftentimes what we'll do is we'll actually take this table and we'll just save it off. I can persist it, and then I can hand it over to some analyst, or a lot of times once you're in this tabular time series model, it actually becomes really easy to use in a variety of visualization tools. I mean, just pick your favorite way to, once you're in a giant spreadsheet, just pick your favorite tool. You can do, trending or projections over time on these values. And so in this case, what we can do is we're just going to save this thing as a new table in our little example time series tables. And then once it's saved off, we no longer have to reproduce the whole thing in our notebook. We can just query the table directly, running the system there. And I'm not going to go super in depth in all of these, but once we have these things, then we can. So here's a simple one. If I just want to compute the correlation between LDL and max triglycerides, for instance, it's just one line. And so, which I think is kind of interesting, again, by creating these tabular building blocks, then we can start answering these questions much more quickly than we could before. And so actually this one, I won't go into this one in depth. For the particularly savvy SQL users, we include like the leg and lead functions, so we can kind of see, do some sort of forward-looking analysis as this sort of thing go. But I'll save that. I won't go into depth in that one. All of this notebook's available online for anyone who wants to take a closer look. And the one thing is that I will reference here is at the last Connectathon, a handful of us, there was actually a group focused on SQL on FHIR, and we kind of took a couple passes at this, and we've kind of came up with this very early draft proposal for how we can natively represent SQL FHIR resources using SQL. The idea being that it's portable between many systems. The things that I showed here in this demo just happen to use the Apache Spark as the processing engine. But there's a lot of really excellent scalable query engines that exist, and I think it'd be great if we're able to take this sort of same SQL and, as much as possible, make it portable between systems. Because really, one of our ultimate goals is to have portable, reproducible research, and be able to make this really easy on SQL users to do. And so I'll include this link in there if you want to dig into the details of the specification as well. If we go back to, finally, the last thing I'll touch on in terms of this demo is in terms of machine learning workloads, which is a growing area of excitement here. I mean, so one of the nice things is that this tabular model, this is really a set, you can view this as a set of really high-level features that could be then plugged directly into an arbitrary machine learning algorithm. There are changes over time, we have what all these are. At this point, we can kind of stick it into, just to pick your machine learning algorithm, you can do additional feature engineering directly in these tools, and build and train the model. And all of this can be done directly in the notebook. So this code here is just showing examples of using the Apache Spark ML library. So Spark itself has a nice machine learning library built into it. But really, the nice thing is that this sort of feature vector is decoupled from whatever tools we want to use for the machine learning workload. So once we've done this analysis, we can plug it into arbitrary other tools for machine learning or any other analysis that we want to do. All right, so we're going to go back to our slides here. So we talked a little bit about our approach to SQL on FHIR. We hit that on the last Connectathon. I think we're going to continue driving forward on this. I'm just going to touch on a couple of our takeaways from how we're approaching this challenge. In that, one, probably the predominant thing is that we really want the experience of the SQL user to win. With regards to, these are our analysts, we want them using the system. We want to create a great, natural, intuitive experience of running SQL over FHIR data. Because if it doesn't feel really natural and easy to use, we're not going to bring these users into this system. We want to be standards-based whenever possible. The nice thing is that the last several versions of ANSI SQL actually has full support for nested data structures. So we can actually take FHIR and natively encode it in SQL formats, with a couple exceptions that I'll touch on a little bit. As part of being really natural, we're actually making extensions first-class fields, because extensions are quite difficult to work with in an SQL language. Whereas if you, instead of, for instance, in US Core, if the ethnicity extension is just a first-class field on the patient structure definition, we can tap into that as well. Part of this is that it does imply that this SQL over FHIR is a lossy view of underlying data in some circumstances. So some things just don't map well. Some things in the FHIR specification don't map great to SQL structures. So for instance, there are recursive structures, or extensions can have extensions that go arbitrarily deep. While it may be possible to take that and map that to some SQL schema, it'd be so difficult and complicated, difficult to use, that sort of conflicts with our SQL user experience. So in these couple cases, the conversion to SQL is lossy. But we mitigate all of that by our approach to running SQL on FHIR is that we can discard and recreate these views as we need them. So for instance, if I know what extensions I have up front, I can generate an SQL schema that satisfies all those extensions. If I discover I have some new extension or some new structure definition or some new profile, I'll just discard my SQL-based view of that underlying data and then recreate it with the new extensions that we have. And I think this is the sort of thing that is pretty important in order to sort of create this view, is to view it as a view of the underlying data rather than the source of truth. Then as we evolve, the ability to discard it and improve it from there. And so to wrap up, we have just a few takeaways there. One is we want that strong separation of data and tools, because these tools are continually evolving quickly. Having this cataloged data lake type thing of everything together, of FHIR resources that we can easily explore it. Efficient columnar formats, which is the nice thing is, since FHIR is a logical model, we can map it onto columnar formats really easily. Structure definitions are the source of truth, and we feel pretty good about that. One thing we didn't mention here is the reproducibility of the system, and the way that we've used it. It's not really coded into the library, but all the usage that we've done is that we never update rows. We basically just create here's what the data looked like at this point in time. So if I have a research workload, I can always reproduce that research again and again. So we basically work with immutable data and can reproduce it from there. And close out with just a couple links that you can work with. So the SQL and FHIR draft is linked there. And then if you're interested in running that interactive demo, you can just go to that website or go to that GitHub repository at the bottom. It's just a Docker container. You can run everything that we showed there. All right, so with that, I think I have like a minute or two left here on time, so I'll open it up for any questions. Oh, up front there.
You mentioned sort of a method of taking extensions.
Yeah. Sorry, wait for it. Yeah.
Thanks for the presentation.
Sure
you mentioned sort of a method of taking the extensions and flattening them out to make it more SQL accessible.
Yeah.
Is that using a similar technique to what was described earlier in the protobuf?
Yeah, actually. So we've been, so some of my friends at Google have participated in the Connectathon, and so we're trying to converge on all these conventions in these places. There's some differences in terms of protobuf is in some ways more expressive than what can easily be done in SQL, but every time there is an overlap, we want to try and follow the same convention. So for instance, for the things like expanding extensions, we're using the same field names, the same structure, and everything like that. I will say that we're still moving towards that, so we're not fully aligned quite yet, but I think we have an agreement on where we want to go, and we'll be iterating on that over the next coming weeks and months. But yeah, the goal here is that we'll be completely converged there over time. Yeah, thank you. That's a good question. Other questions? Yes.
So you have it's great stuff, by the way, but you start with the Cynthia data and some files. Mm-hmm. So if you don't, if you have a giant FHIR server instead with a bunch of data in it, what do you guys do?
Yeah. So and actually what you're describing is our typical workload. Is like, yeah, we'll have a giant in our giant data lake of resources aggregated from a bunch of different things. So the way we actually see that is we actually have essentially it's really just a Spark job that goes through and reads the native resources, in many cases which are internal formats or client-specific formats, and then we just convert them onto the FHIR data model as part of that job.
Kind of initially dump it out as JSON resource.
Yeah. Yeah, well, we don't even actually, in these cases, we don't actually even need to persist the JSON resources, because we basically have our internal data model. We can convert it into the FHIR data model, and then we save it as Parquet. We could save it as JSON resources, but we don't really need to, because we can always reproduce it from the source there. But yeah, and internally, I mean, and you can see the source code of the library. We actually use the Happy FHIR API internally to that transformation. So we'll go load it up. We'll use Happy to kind of do all the validation, everything like that. And then this open source project can take those Happy resources and save them as a Parquet file using that format. But we could easily write. In fact, when we want to share them with other systems, we do save them like as ND-JSON as well. So you have that standards-based data sharing too. Yeah. Yes?
Can you recreate the JSON from the Parquet?
Okay, so I'll repeat it. The question is, can you recreate the JSON from the Parquet? And the answer is yes, with the one exception of the couple. Some of these conversions are lossy. Really the main ones are like one. In the Parquet, we want to use like numeric types instead of strings, so you don't know the precision of the numeric value. And the reason for that is like we have a lot of people writing SQL queries. If we stored numbers as strings, then people do greater than, and they're actually they're doing a string comparison when they think they're doing a numeric comparison. So there's that, and then we don't actually when we store it as Parquet, we basically discard undeclared extensions, simply because we need to know about the extension in order to make it a first-class field. So with those caveats, we can go from JSON to Parquet and back to JSON. But again, we view the Parquet file as a view of the JSON file because some of those projections onto Parquet are lossy for those reasons that I mentioned. So we always keep the raw data, I guess is what it boils down to. Interestingly is that at least for many of our workloads, because we have out-of-band knowledge about the data, that lossy nature doesn't apply. So we know the full set of extensions that we're dealing with. So we know we're not going to lose any of that stuff. But if you're working with just some unknown set of JSON, you want to understand what the extensions you need to project that on first. All right. Any other questions? All right. Cool. Okay, yeah, I'll hang out for a bit if anyone wants to talk as well. But thanks a lot. I really appreciate it.